Section 16.3, the pH scale. Okay, let's take a look at here at a way of representing the acidity of a solution. So let's write that word down, acidity. Acidity is a way of talking about the hydronium ion, the H3O plus ion. When we say that a solution is acidic, what we really mean is that there is more or a higher concentration of hydronium than there is hydroxide. So what we would be meaning when we say something's acidic is that hydronium concentration is greater than hydroxide concentration. Now remember, the product of the two concentrations is Kw, which at 25 degrees C is 1.0 times 10 to the minus 14. So we could have a solution that is basic. By the way, the other term for basic is alkaline. And if a solution is basic or alkaline, that means the concentration of hydronium is less than the concentration of hydroxide. So remember, water has both of these at all times. There's some amount of both of them, hydronium and hydroxide. It's just an issue of whether one is a higher concentration than the other. If the solution has more hydronium than hydroxide, it's acidic. If it has more hydroxide than hydronium, then it's basic or alkaline. Okay? So imagine we take an acid. HCl is an acid, at least in water. As a pure substance, it's a gas under normal conditions, and so we really wouldn't even think of it as an acid. But if you put it into water, it will dissolve in the water, and it will react with the water to form hydronium, H3O+. That's this substance right here, hydronium. And you also form some chloride. Now, remember, the shorthand notation for this is to say that it just breaks up into hydrogen ions, H+, and chloride ions. So we can use those interchangeably. So imagine you've got this water in a cup, and you dissolve the HCl into the water. That will give you hydronium ions, all dissolved throughout the water. Of course, they're very small and they're invisible. You wouldn't be able to see them. But we can represent them by using these little symbols, these formulas. Of course, there's also chlorides in there. I'm not going to draw the chlorides in there. So I'm not drawing the water, I'm not drawing the chlorides, I'm just drawing the hydroniums. Okay? Now, I've shown you the two equations. What we can do is we can do a calculation of these concentrations. And so I'm going to define something called pH, the potential of hydrogen. And it's going to be based on a logarithmic function. Log base 10 of the hydronium concentration. Okay? Now let's remind ourselves a little bit about concentration. This would be the moles of hydronium divided by the number of liters of solution, right? Moles over liters is concentration, or molarity in any case. So the negative log base 10 of the hydronium concentration. You may be familiar with the Richter scale used for earthquakes. The Richter scale is also a log base 10, okay? Let me show you some numbers. This is table 16.3 from your textbook. Benchmark pH values for a range of hydronium ion concentrations at 25 degrees C. So remember, we're doing all these calculations in this chapter at 25 degrees C because equilibrium constants change with temperature. So look on the left. These are different concentrations of hydronium that differ by factors of 10. Of course, they seem to start at less than 1. So the first one is 0.10. You take the negative log of that. Look what happens. The pH on the right is 1.00. You take a tenth of that, 0.01. The negative log of that, 0.01. So notice in the middle, they put it into scientific notation for that one. So it's 1.0 times 10 to the minus 2. That gives you a pH of 2.00. Next one, 1.0 times 10 to the minus 3. Negative log of that gives you 3.0. So what's happening is every time that you make the concentration smaller by a factor of 10, the pH goes up by 1 unit. And that's why the log base 10 scale is used. The pH scale is very convenient. Decrease the concentration by 10, the pH goes up by 1. So higher pH corresponds to lower concentration of hydronium, right? In fact, if you go all the way down to the bottom to a very low concentration of hydronium, 1.0 times 10 to the minus 14, that's pretty small. The negative log of that is 14. And so that's a very low concentration or a very high pH. So high pH corresponds to low concentration. Low pH, 1 or 2 or 3, corresponds to high concentration, 0.1, 0.01, or 0.001. Notice that when you're at 7, that corresponds to a concentration of 10 to the minus 7. That is neutral. So below pH 7 is acidic, above pH 7 is basic, and right at pH 7 is neutral. Okay? Here's a picture of a pH meter. The pH meter is an electrochemical device. These days they're digital, and they can plug right into the solution. So you put a probe into the solution that you want to measure. It will measure using what's called a glass membrane the pH of the solution. So for this one, it says the pH is 2.93. Okay. Now, we're going to be doing calculations in the sample problems. I've shown you the definition of pH as a calculation, as a formula. I'm going to rewrite it here. So pH is the negative log of the concentration of hydronium, or in shorthand notation, negative log of H plus. If I don't put the 10 below the log, that means it's base 10. Okay. What if you want to go back the other way? What if you know the pH but you don't know the hydronium concentration? I'm going to show you stepwise how you would do that. We'll start with our beginning equation here. So the first thing we would do is we're trying to isolate algebraically the concentration of H3O plus in the brackets there, right? So let's get the negative to the other side. So we'll multiply the equation by -1. So you get negative pH. Negative times negative is positive, so you get log of hydronium concentration. Now we've got a little issue here. We've got the log. How do we get rid of log? What we do is called the antilog. The antilog is a base raised to an exponent. So the antilog of base 10 is called 10 to the x. So 10 to the negative pH is equal to 10 to the log of the hydronium concentration. But 10 to the log, they cancel each other essentially. And so you just get H3O plus on the right side. There's our result. If you know the pH, you just take 10 to the negative pH and that will get you the hydronium concentration, which we'll see in example problems.